So good evening. It's a pleasure to welcome you all to the 14th session of Rise Up. Today we'll have our Tharun Krishna leading the session, who will be giving us a peek on the topic, how do drugs work in our body. As we all know, Tharun is an 8th grader and he's being homeschooled. Also, he had a magnificent session earlier where he was explaining how our pancreas worked. Eagerly moving on to his presentation. Tharun, you could start.
Thank you. So I'm going to present today about how do the drugs work. So first of all, I'm gonna a little bit explain what is a drug. Now the first thing, like commonly known, first thing I said to my mother, what is a drug? She usually said about very dangerous drugs such as cocaine, nicotine, alcohol, all that affect our mind, consciousness, brain, then very potentially dangerous drug. So these are called narcotic drugs. So everyone, not everyone, but most of one thinks about when they say drugs. They will say drugs are very bad. You should not take drugs. But scientifically, a drug is classified as any substance that cause an effect when introduced to the body. So medicine can also be a drug, because medicine, when taken or introduced to the body, medicine can also have an effect. So a drug that is used to cure disease is medicine. Now, example are caffeine in drugs, example are caffeine in coffee, nicotine, tobacco, etc. Now, the pharmacology is a field of science of drugs and how they work. My today's topic, how do drugs work? So that thing people study, and that field of study is called pharmacology. There are two main areas or divisions in pharmacology of studying how do drugs work. One is pharmacokinetics and one is pharmacodynamics. So the pharmacokinetics usually describes how the body affects the drug after the drug is ingested, or how the body process the drug when we ingest, and after we ingest, what happens to the drug when the drug is moving through the body. Now, pharmacodynamics deals with the effects of drug, like um, when the drug reaches the tissues, how it works, and the effects of drugs on the tissues, and the mechanism of action. So basically, one minute. So basically, pharmacokinetics usually describes what happens to our drug when it is entered our body, and pharmacodynamics deals how the drug affect the body. Now I'm going to say about pharmacokinetics little bit detail. Now pharmacokinetics, as I said before, are a study of studying what happens to the drug. Now, there are four main processes that happen to a drug when it enters our human body. One is absorption, distribution, metabolism, and excretion. Now, absorption. So absorption is a pretty common process. That means in food, digestive system, etc. So here also absorption is the process in which drug, when taken orally, moves into the bloodstream. So it's a process by which our small intestines take the drug and absorb into the bloodstream. Now, when directly injected to the blood, there is no absorption process because it directly reaches the blood. Now, there's a term here called bioavailability in this pharmacokinetics. Now, this term usually refers to the portion of active drug that is absorbed or reach the main circulation after absorption. So, like after all the drug is absorbed, how many of them reach the main circulation, or how many of them enters the main circulation? That is the bioavailability. For example, it is 100% when injected directly. That means 100%. That means all of them, all of the active drugs are directly reach our main circulation through syringe or vaccines. But when taken orally, many the absorbed drugs, many will not reach the main bloodstream. Now, what they meant here is that I'm going to say example that is not scientifically true, but I'm just going to say for example. So let's suppose there are 10 drugs that reach the small intestine. Now all of the 10 drugs or 10 molecules of drugs are absorbed into the bloodstream. So this is the bloodstream. Now through this process, some of them is broken down and turned inactive. So we lost two drugs by this process. Now only 8 of them reach this bloodstream. Then these absorbed drugs will reach the liver before reaching the main bloodstream for body. The liver also breaks down 3 of them. So only 5 will be entered to the main bloodstream. So out of 10 that we taken, only 5 reaches the main bloodstream. So 5 out of 10, which is 50%, is the bioavailability of the drug. Now, as I'm going to say about distribution. Now, as the drug is absorbed and reach the main bloodstream of our body, distribution describes about the distribution is another process of pharmacokinetics. Distribution describes the journey of drug through the bloodstream to various tissues. It also describes like how much drug will end up on tissue, what all will affect that, what all will affect the quantity of drug that end up on tissues. Now, the one thing is blood flow. That is, if blood flow is larger to an organ, such as normally blood flow is larger to brains, liver, so that drugs will reach to them more likely. So the blood flow affect how much drug will reach an organ. Then anatomical barriers such as blood-brain barrier, which are barriers that are used in our organs and between organ and bloodstream. Now, if there is anatomical barriers, these barriers can act as a wall and block some drugs. Many of the drugs will reach the barrier and go, but many will be blocked by anatomical barriers such as the blood-brain barriers. Now, another thing that affects how much drug that end up on tissues are the interaction of drug with the components of blood, such as proteins in plasma. Now, how it works that some drugs, like warfarin, bind to proteins. That means they're highly likely to bind to proteins. So if they're absorbed, they will bind to protein found on blood called plasma proteins. Now, what happens, what the problem with this drug binding to it is that when the drug bind to plasma protein, it will just stay in the blood. It will just stay with the protein. It cannot go into tissues. Our main role is to make this drug into tissues, right? Because then only the drug can do its effect. So only if the drug is active, it can go into tissues. Like if it is just staying in there with the plasma proteins bonded, this drug will be happy here. It will not go into tissues. So we don't want that. So that's why sometimes the second drug is given in combination with the first drug to avoid this. So the second drug is not that much important. So first drug is important. So what happens is that this is the normal case where first drug just stay here binding to the plasma protein. And second drug is given. This second drug can replace this first drug. Okay, the second drug can says like, okay, you go into the, I will bind to this, you go and free yourself. So the second drug will replace this first drug's position. So second drug is not important, so it can stay here, we don't care that much. But the main improvement here is that this first drug is freed so that it can move to tissues and do its job. So basically, after all the distribution, the drug reaches tissues and do its function. Now I'm going to say about metabolism. So eventually, through distribution, the bloods, I said, the drugs will reach the tissues and do its effect. But over time, this our body, over time, this drug on our body will circulate, right? So that is where this metabolism process take place. So metabolism is a process in which a drug is broken down and turned inactive. So basically our body changes the or breaks down the drug, and when the drug is broken down, it will eventually be inactive. That means it will be effectless. The drug will no longer be useful. Now, why are our body doing this? Because drugs are useful, right? Such as medicines or that are useful. Then why are our body breaking down these drugs? So it is because like our body doesn't know like this drug is helpful. Like, oh, it's medicine, so it's helpful. Then if alcohol comes, oh, alcohol is dangerous. Our body doesn't know this. In perspective of our body, drug is a foreign substance and our body doesn't like a bit. So it needs to break down that drug and throw it away from the body. So the first thing our body do is, like drugs are, it will metabolize them. That is, they will break them down and they will turn them inactive. Then they will excrete these. So this metabolism is carried out by enzymes. The main enzyme that do this is cytochrome P450. Now, when a drug is metabolized, active drug that has effect and that can do many things in our body, if that is metabolized, it will change. The enzyme will change this active drug into metabolites. So metabolites are the result or end products. So these metabolites will be inactive. So that is happen when our body metabolize this active drugs. Now excretion. Excretion is a process where these drugs or metabolites, the product of metabolism, exit the body. Now, one thing I have to say that metabolism has two meaning. Like here, it's the breaking down of drugs, but normally metabolism is a chemical reactions in our body. But in here, I meant about breaking down the drugs and turning them inactive. So our body excrete the drugs in, sorry. So this is in this stage is where body finally get relieved, because finally gets these foreign substances out of the body. Now they do this by four main ways, like exhalation, breathing out, urination, sweating, defecation. Defecation is the solid waste. Now this is the basic of pharmacokinetics. It usually describes how a drug travels through the body and how our body processes them and how our body affects them, what happens to them. Now I'm going to say about pharmacodynamics. Now, as distribution, I said it is how a drug. Now, as earlier I said distribution, that is the process by which the drugs travel through the bloodstream, enter tissues. So like after it enter tissues, before it gets metabolized by the body, it must do its job, right? Because it will eventually get metabolized by our body, because this drug will get circulated through our body. So before getting metabolized, it will first land into tissues. Now after it is land into tissues, it must do its job. That is why drug is introduced to our body. Now, pharmacodynamics deals with this. That means how the drugs work at the tissues, how the mechanism of action, all that study or all that process pharmacodynamics says. A majority of drugs cause an effect. That means this Pharmacodynamics actually studies about the effects of drugs. So the majority of drugs cause an effect or make an effect by interacting with some proteins on our body. So the major proteins will be receptors. Now just recall, receptors are proteins found in cells. Some can be in the cell membrane, the outer layer of our cells, inside the cells, such as in cytoplasm and inside the nucleus, etc. Now, all the receptors, such as the receptors found on this outer cell membrane, will have a ligand. That means ligand is any molecule that binds to them. Now, when a ligand is bonded to a receptor, it will cause a signal, and that signal will cause an effect on our body. For example, it is insulin receptor is here, and this insulin is a ligand because ligand is any substance that binds to the receptor. So the insulin actually binds to the receptor. So even though insulin is a hormone, in here insulin is a ligand which binds with the receptor. And so what happens if ligand bind to receptor? It will cause a signal that also happens here. And after the signal, this will cause an effect on the cell, such as taking in glucose. Now, the role of drugs actually comes here. That means drugs when introduced to the body and distributed and eventually reach the tissues, they will interact or bind to the receptors on the cells. So this is the receptor. This drug will bind to the receptor. Now, so here the drug acts as a ligand because it attached to the receptor. Now, when a drug is binded or bonded to the receptor, it will cause two main things. So there are two main things that can happen when a drug binds to a receptor. One thing is that drug can be agonist. That means, for an example I'm taking, this is insulin and this is insulin receptor, and insulin binds to them and it will cause a signal. So here, insulin is the body's natural or actual ligand because it's the our body's real ligand, right? Now this will cause a signal when insulin binds to insulin receptor. Now here is where the drugs come. So some drugs, this drugs that act as an agonist, comes as a ligand and bind to the insulin receptor. So it acts as a substitute for the real ligand, which is our insulin. So insulin is actually a real teacher. So insulin taken a leave so that the substitute teacher, this drug, can come in and bind to the receptor. And as these drugs and the actual ligands have some same molecule structure, they will bind perfectly to the receptor and that will cause a signal. So that will cause the same effect as when the actual ligand, the insulin, binded to this. So there are no change. So this is what agonist drugs are. That means these are drugs that bind to a receptor and mimics the actual ligand. In here is the insulin and causes the same reaction as the substance that normally binds to the receptor. So these type of drugs actually carry on process, such as when insulin is not there, drugs can be introduced because these drugs mimic the insulin and bind to this. So even if insulin is not there, this drug can take over the action of insulin because it binds to the receptor perfectly. It causes the same effect. I started talking about how drugs work, and I started about the two things that happen when a drug interacts or binds to a receptor. So one thing is that drug can be an agonist, so that that means it can mimic. So I say, so agonist drugs can bind to a receptor, and that means it acts as a substitute for the actual ligand in our body, and that causes the same action, and the natural ligand causes. Now, the other thing that can happen is that a drug can be antagonist. That means that these drugs, just like agonist, will bind to a receptor, any receptor, but does not activate it. That means the drugs. I'm taking insulin as a common example for all. So insulin receptor is here, and this drug introduced to our body will come and bind like this, but it is not just perfect enough to activate it and cause a reaction or cause an effect. But so here it may not see as a big deal because it's just binding, nothing has happened. What is happening is that this drug is blocking the actual ligand from binding to the receptor. That means it is blocking insulin from binding to its receptor, insulin receptor. So if insulin doesn't bind to insulin receptor, it will not cause a signal, which in turn will not cause any effect. So antagonist drugs are drugs that block the actual ligand from binding to its receptor, eventually blocking the whole effect of the actual ligand, because only when actual ligand is bound to a receptor, it will cause an effect. Now, there are two major ways of these are just two major ways of how drugs work, but there are still a whole lot ways how drugs work. But I just said just two basic things. Now, with all these pharmacokinetics and all the things that I have said, I'm just saying an example of how some drugs work, how a drug works. So that drug is caffeine found on coffee. So with all the above information, I'm going to explain about the pharmacology of caffeine or how caffeine works. Now, I'm going to first say about pharmacokinetics. Now, caffeine is absorbed. The first thing pharmacokinetics is absorption. Now, caffeine is absorbed by the intestine within 45 minutes after it reaches after our, after we take caffeine. Then the second step, distribution. The caffeine is distributed all our body and all of our tissues. Now, the third step is that metabolism. Sorry, metabolization. Now, the thing is that the caffeine, so here is the effect, okay? Caffeine's effect is here when it is distributed into tissues, but eventually the caffeine get metabolized, which is the third process of our pharmacokinetics. Now, caffeine is metabolized in the liver by CYP1A2 enzymes. Now, as I said before, when a drug is metabolized, it will change or it will be changed into metabolites, that is inactive form of them. So the three are paraxanthine, theobromine, the one you see in chocolates, and theophylline. So these three are the metabolites or the end products when the caffeine drug is metabolized in the liver. Now these metabolites are excreted through urine. So this is the pharmacokinetics of caffeine. Now the interesting part, pharmacodynamics. So people say is that if you drink coffee, you will feel awake. You will not feel drowsy. You will, such as when you have work at early morning, drink coffee. It will help you from feeling sleepy. So people say that. So it's basically due to the caffeine drug in it. Now, but the question here about in pharmacodynamics is how caffeine keep us awake. That means how caffeine does its effect. So this is a caffeine molecule. Now to understand how caffeine works, I will say about the normal process in a person. So normally in a person awake, not sleepy, a person awake in morning with no caffeine, they have a little adenosine in the brain. So adenosine or 1 minute, adenosine is a molecule basically. So you can recall this from ATP, our energy currency of the cell, the same molecule of the ATP. not ATP, but adenosine is a part of ATP. So normally in a person awake, as I said before, they have a little adenosine in the brain. So adenosine molecules will be present in the brain, but it is usually low when a person is awake. So this is our brain, this oval shape. Now adenosine here is awake present, that means just two of them, just little. But over time, the adenosine will accumulate, increase in number, and it will just fill up the, not fill up, but it will increase in number in the brain. Now, as it just increase in number, this adenosine as a ligand, natural ligand, will bind to the receptor. So what happens when a ligand binds to the receptor? It will cause a signal. So when adenosine binds to this receptor, it will cause a signal that eventually makes us sleepy. So basically, it is this adenosine that causes the sleepy when it's bound to receptor. So what we have to do to prevent our sleepiness? As I said before, only when adenosine is bound to its receptor, we will feel sleepy. So just think, why can't we block this process? Like, why can't we block this adenosine from binding to the receptor so that the sleepiness will not occur? Because only when adenosine bind to receptor, we will feel sleepy. But if we block adenosine from binding to its receptor, we will not feel sleepy, right? So that is exactly what caffeine does. So caffeine is an antagonist, meaning it will block the actual ligand from binding to its receptor. So this caffeine actually interferes it and claims this caffeine comes here and bind to adenosine's receptor. So what happens is that adenosine, our body's natural actual ligand, cannot bind to the receptor. So if adenosine cannot bind to the receptor, it cannot cause an signal. So if it cannot cause a signal here, we will not feel sleepy. So as caffeine is an antagonist, it just binds here, it doesn't activate the receptor. So this is how caffeine works. So it basically acts as an antagonist, meaning it blocks the natural ligament, adenosine, from binding to a receptor. So if adenosine doesn't bind to the receptor, we will not feel sleepy, because only when adenosine bind to the receptor, we will feel sleepy. So that is the pharmacodynamics of caffeine. So like this, you can tackle or you can understand as many as drugs with this pharmacology, with what is the pharmacokinetics of drugs, what is the pharmacodynamics of drugs. So with this, you can actually understand the whole process of what happens to a drug when it enters our body. So that's my presentation. Thank you.
Yes, Tarun, it was a nice presentation. So those who have doubts, you can ask to Tarun or you can give feedbacks.
ഡ്രഗ്സ് യൂസ് ചെയ്ത ഞാൻ ഇന്ത്യയിലുള്ള നിയമങ്ങൾ ഉണ്ടല്ലോ.
അത് ഞാൻ നോക്കിയിട്ടില്ല, കാരണം ഞാൻ യൂഷ്വലി സ്പെസിഫൈ ചെയ്ത് ബോഡിയിൽ എങ്ങനെയാണ് ഡ്രഗിന്റെ റൂൾസ് എന്നാണ്. പക്ഷെ ഗവൺമെന്റ് റൂൾസ് ഒന്നും എനിക്കറിയില്ല.
So Tarun, many people say, when you take painkillers on a continuous basis, that really harms the body. Like, you want to throw some light into that? Like, they used to use opium sometimes as painkillers, kind of stuff. So heavy drugs.
Yeah.
So what is actually happening when you take such kind of stuff for a long time?
Like how painkillers work?
Yeah, so when you take painkillers quite often, it is learned that it really affects your body organ system. So what would be actually happening?
I don't know the negative effects, but what just happens that I watched a video very time because I have not clear explanation, but I heard this actually this painkillers block our pain sensation so that our brain doesn't receive any pain, so we feel okay, our pain is gone, like that. We feel pain because the pain receptors gets activated and gets pain, right? So these painkillers actually block these receptors from being activated, so we'll not feel pain. So pain is still there, but we don't just feel it.
I think nobody have any doubts. So let's wind up the session. So before that, our next session is on 23rd of January. So it's a debate. So I welcome all of you to that session. And after we have presentation by Meenakshi on February 12th. So Meenakshi is here, I think. So can you tell your topic?
Yeah, so I'd like to speak on feminism. I'll be talking about what is feminism and give a quick rundown on the history of feminism and on the most common misconceptions of feminism.